thought about overnight? I'm not going on to that yet, Tim. I do need to go out. So, I'm going to talk about supportability audit. And what do I mean by supportability audit? And why have I said there's gold in them there hills? Which is a particularly American phrase that emerged from the days of the gold rush, when people heard that there was gold in the mountains. And everybody rushed, first to California, then to the Black Mountains where Custer was killed, and then up into the Yukon in northern Canada to find gold and make their fortune. And there are two ways in which they could find the gold. Firstly, they could sit on a riverbank with a saucepan and try and pan for gold, as it's called, which is stick in a pan, sift the gold, sift all the silt, see if they could see any gold, throw it away, get another one. And they could spend months and months sitting in the freezing cold and find absolutely nothing. Some people got rich, but very, very few. The clever people looked at the ground and the geology, and because they understood what the structure underneath the ground was, they knew where the gold seams were. And they dug to the gold seam and said, this is mine. So in South Africa, where the biggest gold mines in the world are and the biggest diamond mines in the world are, you don't see people sitting on a riverbank doing this. They find the gold seam and dig for them. So what this is trying to say is supportability audit is how do you find the gold in the best possible way to give you the maximum return to make systems more supportable. Okay? That's what the phrase means. Okay. 2 minutes on TFD. Tools for decision, but we always call ourselves TFD. I'm not going to do a big sales pitch. The TFD mission is to optimize the cost and availability of supporting complex equipment systems or fleets that require maintenance. And this is where it is important that there is maintenance activity on the system and some items get repaired. It is not one-way pipe logistics of the cabbage from the field or the coat from Bangladesh to a shop. There is a reverse supply, a reverse process, a feedback loop that requires maintenance. That is what our capability is, to work out how to optimize it. As an ex-Royal Air Force officer, this phrase, this quote is particularly relevant. And the Royal Air Force in the UK, as the oldest independent air force in the world, is 100 years old this year. And Marshal of the Royal Air Force, the Lord Trenchard, was its founder, and in his very first inaugural address to the Royal Air Force Staff College, very nearly 100 years ago, he said this thing. Remember, the one thing that you should turn your mind to, and he was talking to the future leaders of the Air Force, is at all times to increase the power of men and materiel without increasing either. Increase the power of men and materiel without increasing the number of men and materiel. Very, very powerful quote that is true today, not just for the Air Force, but right the way across this area, as it was of saying that is that our job is quantified modelling and analysis that will support logistic decision making. So quantified modelling and analysis to support logistic decision making, increase performance, reduce cost, whilst mitigating the commercial and the operational risks. So we use modelling to drive up performance, drive down cost, while thinking about all the risks on both sides. Lots of words. There is a nice simple way of saying it. Do more with less. Through smarter ownership. Do more with less through smarter ownership. That is what we help our customers to do. And it doesn't matter whether our customers are on the government side or on the industry side. It doesn't matter to us, we can do either. Way back in 2008, just after I left the Air Force, I was asked by the team leader for the RAF Chinook fleet to come and give him some hand, and he knew me of old, so he said, well, can you come and help? The problem is this: in Afghanistan and Iraq there is severe pressure for greater output from the Chinook fleet for more hours, more flying hours, on both operations in Afghanistan and Iraq and in training. The RAF was able to achieve 65 flying hours on each of these aircraft on operations, but only 40 on training. And it's the lack of hours on training that was holding back the ability to deploy more aircraft. They couldn't train the crews fast enough. And yet some civilian operators of the Chinook aircraft were getting 200 hours per month. Now, if you set aside differences in the environment and the equipment and the like, nevertheless, there was still considerable room for improvement, and he was under huge pressure to achieve it. His question: how do I increase fleet flying from 12,500 flying hours in each year, to 16,500, to 18,500, and eventually to 21,000 flying hours? He actually wanted to go to 25,000. Okay, so I was sent off to go and ask that question. I was back in his office within 36 hours, and I said, SOS. He said, what? I said, SOS. He said, is it really that awful? It's an emergency. I said, no, same old stuff. It's the same old stuff that has stopped you getting flying hours as it has done for the 30-something years. It's the same things: people, resources, management, policies, plans. Those things are stopping you, as they always have done. So I went away to prove it, and the method was what has become supportability audit. Firstly, I conducted about 76 structured interviews with everybody from the 2-star air marshal who was commanding Joint Helicopter Command, to the station commander, to the pilots, to the engineers, to the logisticians, to the tradesmen, industry, everybody. Because they knew what the problems were. They knew what the problems were, but they couldn't prove it. So I went and collected a lot of data from where I could and analysed it. Lots and lots of data. The problem was, it's all very well having data, but data is historic. If you build a model to test your hypotheses of what could be done, you can see what might work and what won't work. So I built a model to test the hypotheses, worked out what actions might work, and constructed a coherent action plan. It took between 3 and 6 months to do that work. It was very lengthy. However, through a series of actions, I concluded and persuaded the Royal Air Force that they could get 39% more flying hours out of their fleet. They didn't take every action, but they took a lot of them. And within 18 months, they'd gone from 12,000 hours to 16,000 hours to 18,500 within about 18 months. At which point they stopped and said, actually, we've got enough flying hours now. We'd rather take airplanes out of the fleet and modify them for more capability than push on to 21,000 flying hours, which was possible. So the plan was proven. Okay? Because of the success, the Commander Joint Helicopter Command asked me to go and look at another one of the RAF's helicopter aircraft, which is the EH-101 Merlin. This aircraft was not on operations, and so it had no complication of operations. It was in the UK, it was flying routine training, but it was still only getting 60% of the annual flying task requirement. The problem is that 62% of the fleet was unserviceable. Less than 40% of the fleet was serviceable each day. And that is not uncommon to find that. The issue was that 38% of the fleet was awaiting resources. So the difference between the two was actually it was in work. But because there was so much waiting for resources, the lack of resources was complicating the management, so things were taking longer in work than they should have done, because they're working on this, stop. Work on this, stop. Go back to this one, stop. Go back to that one, stop. And it was just awful. So the question, how do they get, and what do they have to do to achieve the flying task? Same old stuff. Went back, did exactly the same thing again, and concluded that in this fleet they could get 32% more flying hours and 13% more serviceable aircraft, and put 4 aircraft away in a hangar because they weren't needed. It would get more flying out of fewer aeroplanes because you could stop doing the calendar maintenance on a bunch of aeroplanes you didn't need. Just work on the aeroplanes you needed, put the other ones away. They're in short-term reserve. You could pull them out tomorrow, but just don't touch them. That meant your manpower was more efficient. So 39% on Chinook, 32% on Merlin. What I did is there was, in general, 6 interconnected themes of problems. Firstly, the plans, which I mean the contracts and all the commercial management, there was far, far too many separate, incorrect, not properly connected contracts. There was 36 separate project teams responsible for providing parts to Chinook, which was its own project team. The contracts were not a coherent requirement to produce aircraft availability. There were just lots and lots of bits. Secondly, the maintenance policy was out of date. Far, far too much maintenance. And he managed to move a major, which is the biggest strip down, tear down overhaul, from every 2,400 hours to every 3,600 hours. Changed the maintenance policy. Massive reduction in maintenance effort. Also completely changed the way the flying pattern was managed and the servicing policy, the day-to-day servicing policy of the aircraft, so that it reduced the amount of maintenance. We looked at all the spares and said we can reduce the things that are causing aircraft on ground and back orders, i.e. we're waiting for parts, and reducing cannibalisation, robbing between. I've got an aeroplane here that's broken and an aeroplane here that's broken, but if I take the part I haven't got off the other aeroplane, I get one aircraft out of the two. Doubling the amount of maintenance man hours, but getting an aeroplane. All due to not having the right parts in the right place. Hold that thought. I asked them to calculate for me what was the capital value of all the parts on the main operating base that were broken but could be fixed but hadn't been fixed. In other words, the capital value of the broken stock that they should be able to repair. It was £32 million of broken stock. And said to them, you can do better by fixing this stuff and in the right order. And it was driven down to 25 million in 3 months. I'd learnt this from when I commanded my own engineering wing, and we had a similar number of about 32 million of broken stock, and we halved it in about 3 months. But in that case, I was in charge of the bays. In this case, I was merely a consultant. So sometimes with a bit of a boot, you can make things happen faster. Because of all this stock and things in the wrong place, did a complete review of what spares should be where, by location, and said, how many of this do you need to hold? How many of this do you need to hold? How many of that do you need to hold? Which is what is meant by working asset levels. Not stock that's broken, stock that's working. As part of that, we found that 33% of the bill of materials of the Chinook was not within Boeing's contract, Boeing's PBL contract. The project team had thought it was 10%. But because of this first issue, they had no idea. Nobody had any idea. Not Boeing, not the project team, not anybody, that there was a huge gap between the expectation and the contract, and nobody was managing 33% of the spares requirements for the aircraft. No wonder they had problems. Then said, well, you need to look more about what you're actually doing with the aeroplanes. And there's a hum system on the aircraft, on Chinook, and on Merlin. But on Chinook, it had been there for probably about 20 years, because I wrote the requirement to put it there myself 25 years ago. They had 85,000 flying hours of health and usage data that they had not analysed. So they had all this data about the use of the aircraft, and they hadn't used it to calculate how many spares, how many people, what the maintenance policy should do. They were just recording it and sticking it in a file on a computer and leaving it there. And then finally we said, why is it taking people so long to fix the aeroplanes? Well, it's because the technical publications aren't right, the procedures aren't right, and some of the technical procedures, and this is a classic one, which is an uncommanded flying control maneuver, which is a really serious thing in an aeroplane when suddenly the aeroplane moves and the pilots have not moved the control column. Something has caused the aircraft to go, ugh. That's really worrying and really serious. There was a procedure on Chinook that took about 2 months to work out what was going wrong. We managed to reduce that to under a week by thinking about it and doing the work. So there was no single silver bullet or no single gold nugget, to continue the analogy of the gold in the hills, that solved the problem. Lots of little things, but the synergy between all the things really mounted up to something significant. So what did we do? We took modelling as an enabler, this is what I originally did, and said, let's look at the total system, and let's look at what ifs we could do in the model, which means I didn't have to experiment on the real flying operation. That makes it cheaper, faster, you can fail, and it's more conclusive. Trials can be very uncertain as to whether they actually deliver what we think they're going to deliver. We were able to balance the task and resources, the resources, facilities of people, and see what would work, find out where the constraints were. You could just play with the system and say, I've pushed a bit hard on the model and the whole system's fallen over. where's the critical constraint? Where's the critical resource to do something about it? And then we could identify and quantify the best things to do. But when I did this on these 2 aircraft, this was all based upon talking to people. And I suddenly thought, if we have a data model of the aircraft, I can ask the model in a report. That's the same as having an interview with the people. So why, instead of asking the people, why not ask the digital twin? Create a model that is the digital twin of the logistics and the system, the total system, and ask that. That is the fundamental source of supportability audit. The technique was established manually, and all that's now happened is we've developed it into data and an automated process. Okay, what do I mean by this? I say, let's take a source of data that we use for planning. We model it and use that to make decisions of the support plan, which become your baseline plan. Unfortunately, the baseline plan, the real world, is never going to be the same as you planned, and the real world will throw you reality in the data that's different from the data you used to produce your plan. Therefore, you need some form of tool, of method of comparing your plan with reality to see where it's different. But what you must decide is whether the difference is important or not. If it's not important, recognise it, live with it. Because there's no point in doing anything about it. Fine, you can change the data in your model, but you don't do anything. But if you need to do something, what do? You remodel and replan, and that is a control loop. So supportability audit, and we use our supportability workbench, which is a range of tools, both to plan and to control the system. So we build a common support planning data source. You build a model, and you look at all the various contracting options of what you might do differently and how, and you set your baseline plan. Once you've built that, you have your digital twin. So don't lose it, which is what most people do. They build the plan and they lose the underlying data, and they just operate the plan. Well, if you use supportability audit to find the problem areas, and then you can identify and explore the benefits and costs of the solutions, you can apply active management control to identify what you should do, in what order, in what timescale, to avoid the support system failing on you. So supportability audit is a technique to enable Kaizen. Okay. Let me take a very, very simple logistic system of an aeroplane on which something breaks, it's removed and replaced, and that rate at which it needs to be removed and replaced is called the demand. The item is probably replaced with an item from local stock, which has a cost to put in there. The broken one, do you throw it away or do you repair it? If you throw it away, there's a cost to buy a new one. If you decide to repair it, do you repair it locally, which is a short loop, but you need piece parts to be removed and replaced, which cost, and they need to be replaced? Or do you send it back to the manufacturer in a reverse shipping time, which is back to the manufacturer, who charge you a price for it, and it costs them to do all this, and then they send it in an outward shipping time, which costs money to move things around as well. So the key here is the rate and pattern of use of the system drives the activities at various locations. Each activity at each location takes time and resources, which mean cost. Activities and delays determine the availability. It's a very, very simple logistic system, but they're all like that. There's another way of looking at it. If you have a system, an equipment system, it can fail. But how often it fails depends on how you use it and the sequence of operating events. And an operating event may be a mile, a day, a cycle, a landing, a shot, a submersion, a fly-out. It can be all of those at the same time. When you put that operating event together with the design and how it can fail, which comes from things like Formica's, you can do task analysis using reliability-centered maintenance to determine what your maintenance plan should be. This is the maintenance event. That's your maintenance plan. This must be maintained preventatively at this time. Okay. You then have to decide where you do that maintenance. Each maintenance activity. Do you do it here, or you do it here, or you do it there? That is an economic calculation as well. Once you've decided that, you can define all your resources, all of these things here, by location and write them down in a support plan. The problem with the support plan is the real world is different, and your captured support and maintenance data may tell you something different. So if your plan is not achieving what you want it to achieve, or just as valid, you find you could do it better through Kaizen, could it be that your resources are inappropriate? Too many or too few, which is why this is not achieving what it should do. That's this loop, support management. If your support resources are perfectly tuned to your maintenance, then you have to ask the question, is your maintenance task right? Because something is causing you not to achieve the availability and the cost you want, or you're looking for an opportunity to do better. And if you change this, of course you have to change this. So there's a control loop and a control loop, which implies that one. If neither of these things will fix your system, you probably have no choice but to redesign the system or use it in a different way, or live with it. So this is the same process, just expressed in a different way, connecting the use of a system, the design of a system, with the support of the system, together with the feedback loops. Supportability audit is a way of looking at that. It's the interrogation of the digital twin that is captured by the data that is presented on this picture, that underpins this picture. Supportability audit looks at that data. Okay, we use a particular tool that we call MAP, and I want to just very, very simply explain how that works. If you have a series of operating events, and I've talked about what they are, those operating events can have resources attached to them. A flying hour requires a pilot and maybe other members of the crew. It requires fuel. It requires air traffic control. It may require other things associated with the operating event. Operating events operate on the system, but if you're talking about a landing, it may operate on a specific subsystem. They're on the system, but actually they operate on one subsystem, but they don't affect the radar. But they do affect the landing gear. So they're on systems, at units, because they're different units, at a periodicity, usage, hours, shots, days, miles, and all of them all at the same time. Consume resources in a quantity with a certain probability. Sometimes you use it, sometimes you won't, for a time, and at a cost defined by those resources. Those operating events operate on this system, and the system has a breakdown structure, and the system and the operating event affect different parts of the breakdown structure. In affecting that breakdown structure, then create a requirement for maintenance. And maintenance can be at different levels. If it's a landing gear, it only affects this system and therefore these are used, but the radar is that one, so it works at different levels. Maintenance events are either scheduled or unscheduled, preventative or corrective, at any level of indenture, at units defined by the support policy and the level of repair analysis, consuming resources in a quantity with a probability for a time at a cost, which is what these are. However, one of the most critical resources is people. People require skills, skills require training, training requires a course, which requires facilities, tools, test equipment, and the like. And the turnover of your people is a consequence or has an effect on the resources. If nobody turned over, no churn in your people, no need for training. Never happens. So basically, this is what we are capturing in the model. So let's take, over a period of time, a profile of events and resources. All of these operating events describe the usage of the system, however you want to use it. They generate a requirement for maintenance events. They generate a requirement for training events, and all of the above generates the requirement for resources. Now, what we've done here is deconstruct the entire system to the lowest possible level of maintenance. Suppose you need to change a wheel on an aircraft. It doesn't matter why you need to change it, which could be because the tyre's flat, or it's worn to limits, or it's burst, or it's cut, all of which could be caused by different things. Doesn't matter why it's happened, you need to change the wheel. Why it's happened and the frequency at which it's happened come up here. What you need to do comes down here, which is change a wheel. To change a wheel, you need a new wheel, a jack, a person, some grease, some locking wire, and the person needs to have had some training. That is a cost atom. It is an indivisible set of data that describe a maintenance activity. You can't do it for less and it will never take any more. It's just that. If you take all those cost atoms for every possible maintenance event and add them up, you can get to, in a constructed way, a cost breakdown structure or a chart of accounts, ultimately the life cycle cost. The clever bit, though, is you can add them up in very different ways. Because these cost atoms are life cycle cost atoms. There's a cost associated with an atom. You can add them up by system, subsystem, and sub-subsystem if you choose to do that. Or you can add them up by suppliers. Which suppliers are causing me my cost? Is it these suppliers or those suppliers? Or you can add them up by budget structures. The ACLA pays for the parts. The JASTF pays for the people. So when commanders and budgeters want to understand who's paying for what, actually the truth is still here. It's how you add them up is important to those people. So what MAP allows us to do is add them up in different ways. And effectively, MAP is an event-driven, activity-based adding engine of cost atoms to give you a life cycle cost. And because of this, it handles automatically all those really complex interactions between people, delays, parts, money, all get sorted out in the big adding engine. Because you're just adding up atoms. It's relatively simple. Right, that's how the tool works. So if we're going to interrogate the digital twin, we have a map model operating events, maintenance events, training events, resources, frequencies, durations and costs, the cost atoms. We can add them up. And if you add them up, according to a usage pattern, it gives you the life cycle cost. However, you've added it up, but suppose you do it the other way around and drive down. If we use one of our utilities to interrogate what's going on, post-processing utilities, we can find the events and cost atoms that give us opportunities to reduce the life cycle cost and improve availability. And I'm going to explain how you do that. Supportability audit is a technique to use this data, not just to add it up, but turn the problem around, drive back down again to find the sources. There's a better slide here for this one now. And that allows us to do things that will give us more availability and less cost. Not more availability, more cost, more availability and less cost, if you choose the right things to do. Supportability audit is a technique. It's not a tool, it's a technique. To take all of that data, drive down analysis, and evaluate the improvements. Let me explain how that's going to work, how that works. In this picture, the graphs are how often does it fail, the axes are how often does it fail, how long does it take to repair. Light bulbs are here. Fail often, take very short time to replace. An aircraft carrier ship propulsion shaft that requires a dry dock takes an enormous amount of time to do, but you hopefully don't do it very often. Okay? Each one of these dots is a maintenance event, a cost atom. And I've just plotted here the failure rate against the time to repair. This is a very, very typical picture. Almost all systems I've ever seen look like this, with most things hugging the axes. And this line, an isoquant, is a line of constant impact. Every system I have ever worked on has things out here, and everybody who's ever worked on that system knows exactly what they are. I know what they are on a Phantom. I know what they are on a Chinook. I know what they are. I remember now because we know them. Each one of the people in the room who's worked on the system will know exactly what they are, but they can't quantify them. They can't produce a business case for them. So this is what this picture is showing. This is raw data from the digital twin, just plotted this way. These dots here are the ones that are causing you the problem, because they are failing too often and take too long to repair. Let me take this a little further. Same principle, same pictures, they all look the same. This is the frequency of that maintenance event against the cost of it, the sum of all the resources need to do it. You get a different set of dots in a different set of places. But that tells you the impact of maintenance events on cost. Come to this one. You do the frequency of maintenance events against the duration of that maintenance event, how long it takes. This one, different set of dots, different set of places. This one will tell you your impact on downtime. This one says the frequency of maintenance against the delay in getting the bits you need. You never buy every possible spare that you could ever want such that there will never be a delay. You never have hundreds and thousands of people so that you never wait for maintenance manpower. Or you never have a requirement to wait for information from the contractor. There are always parts of the system that you will have a delay on. It would be inefficient to do it any other way. But those delays are attributable to specific maintenance events. Two things come from this. Firstly, these are the components of the standard cost and availability equation. Availability is uptime over uptime plus downtime. Or availability is the ratio of uptime over uptime plus downtime in terms of plus delay and cost. When you put them all in a sort of magical three-dimensional plot, there's the systems that are really causing you pain. This one down here probably isn't causing you a great deal of pain. You could do something about it, but focus on these ones, because these ones are causing you a problem in every single area you're looking at. Cost, availability, downtime, delay. Okay? That's how it works. But let me go back to this one. Suppose you wanted to do something about these three dots here. And I don't know what to do about it. If anything, should I do something about it? Okay. Let me suppose I can make this system quicker to repair. When I used to work on Sea-King, or the new Sea-Kings for the Air Force, some idiot of a designer put the main radar transmitter under the floor of the rear cabin because there was a big space there for this big radar transmitter box. The problem was it was a search and rescue helicopter and they had to have a rubber floor to stop the water getting into the fuselage. And it took about 8 hours to get the rubber floor up before you could open the panel to get to the radar transmitter. Change the radar transmitter in an hour, put the rubber floor back. And I said, stop, I'm not having it. I want a hole in the rubber floor that you can open quickly and seal. And they went, it can't be done. I said, how on earth do you get into a wetsuit or a dry suit? Of course you can do it. Just go away and do it. The maintenance time for that event was cut from about 16 hours to 1 hour. That's what I mean by that one. This one, suppose you can reduce the failure rate. Okay, we had a low rate transmitter, a highly failing transmitter, changed one of the transistors for one with a higher spec, poof, MTBF went up. This one was a combination of the two. But at this stage, I know these sorts of things can be done, but I don't know the answer to the specifics. Now, typically, engineers go away and come up with bright ideas of what they could do, and then they work out whether it's worth doing them or not, and they work about the business case later. And I say, stop, stop, stop. Don't do that. Just in the data, assume you can move that one from there to there, that from there to there, and that from there to there. Just assume you can do it. To some new numbers. Put the new numbers into the digital twin. Rerun the digital twin. What's the difference in the life cycle cost? Now the project manager is in the position where he can say, if I do these three things, I can save $10 million and improve system availability. Engineers, please come to my office. I'm going to ask you to do these three things for $6 million. Because I know you'll never do it for 6, and you'll probably come back and you'll overrun, so it'll actually be 8. But if you actually finish up doing it for $8 million, I save money. If you can't do it for $6 million or $8 million, don't bother. Because if it's going to take you $12 million to do with it, I'm going to live with this, and I won't bother looking at it again. Unless something changes. So what you are doing here is you are working out not the costs and then the benefit. You work out the benefits and then the costs. And you use the benefits to drive the costs. What you're doing here is in the act, don't act decision, you're filtering out everything you shouldn't waste time on. And build the business case for the things you should do before you start. That is not the way normal engineering in the support world works, but it's the way it should work. Supportability audit is giving project managers, project team leaders, the ability to drive in the discipline of stop doing things that are interesting and do the things that are important. If you compare the previous system lifecycle cost with this assumed future system lifecycle cost, you get the business case benefit. That is what supportability audit allows you to do. Take the data, find out where the things are, you've found the gold seam, work on that and work out whether it's worth bringing out of the ground or not. Okay. I'm now going to give you 3 examples of where I did it, because you want some proof. Yet another RAF helicopter. Okay, but that's just circumstance. We took this helicopter and we took of the 42 Puma aircraft, which is the Eurocopter aeroplane and it's used in Japan. We took 3 aircraft on each of the squadrons, off them, parked them in a hangar, in the digital twin. We didn't have to argue with the squadron commander that he couldn't possibly do it, and he wasn't going to have it, and we weren't going to do it. Didn't even bother. I never even went to the main operating base. I worked in the digital twin. And said, if we did that, we could actually not only maintain the flying task in each unit, but each aircraft could fly more sorties, as you would expect. But each aircraft was doing more. So you could park these aircraft. Incidentally, the operational availability went up because you were using the aircraft more and they were nice and warm and kept warm and the aircraft availability went up. It's a strange perversion of aircraft. Their systems do that. The more you use them, the less they get cold and therefore they don't leak. We said, okay, let's look at the benefit of giving maintenance staff additional training and changing the maintenance procedures to reduce maintenance task durations by 15%. What I was doing here was saying, actually, the most experienced people have already gone down the learning curve. The more experienced people actually already do it 15% shorter than most people. It's the new people that take the time, so the average is elevated. If you could take all the knowledge out of the old people and give it to the new people to drive them down the learning curve faster, that's the sort of benefit you can get. There's actually very little academic evidence of maintenance learning curves, but there should be. But actually that's not unreasonable. We then said, the aeroplane's getting old, so there's a lot more spares that are being ordered for the very first time. Well, why don't we do a strategic review of the things that are likely to come up over the next 3 or 4 years and think now in a piece of work about what you'd have to do to reduce the production lead time of those items by 15%. In other words, do almost an obsolescence, a diminishing manufacturing supply type activity, so that you can, when you need it, you get it quicker. And then we said, hang on a minute, we think you should be moving from a pricing structure, contract structure that incentivizes you for poor reliability, to a pricing structure that incentivizes you to improve reliability, which we can do through PBR. 15% reduction on purchasing and repair prices. It can be done. In fact, you can do more than that. And then finally, we said, well, why don't we take all the unplanned corrective maintenance and reduce it by 15% by properly doing RCM again? All of that has already been done on other aircraft. The consequence of all of that in the model was a 23% saving in the annual support costs of that helicopter, and 5% increase in availability, and the same task with 6 fewer aeroplanes. It saved 5.6 million. The work cost less than £50,000. What's the return on investment for 5 million to £50,000? Massive. But this number, that massive impact on the support costs, was, whoa, people in the UK really waking up to this. It's the first one we did. I never went to the station. I never talked to anybody who was actually operating the aircraft. I did it from the digital twin. The conclusions were underwritten by the team leader for the Puma project saying, he spent a long time on Puma, said, yep, yes, that can, okay, I believe it. We went to Sweden. And from here we went from a helicopter to a vehicle. And when I explained to the Swedes what we were doing, they said, we don't think you'll be able to help us. Let's give you this example of this vehicle. This is a Mercedes Geländewagen, which is a truck, a small SUV militarised truck. It's been in production for 36 years. Over 200,000 have been built, and the whole system is fully supported by Mercedes. I bet you can't find savings in this fleet. Oh, by the way, it's only used in training, so there's no operational impact. You won't find any savings in that. Okay? We'll see what we can do. What we first of all found is that the vehicle utilisation was extremely low. And you could take 70 vehicles out of the 347 and put them in a shed and not use them. You'd still pull them out, and within 2 hours you'd be ready to use them if you had to. But the point is, the general liked to see a nice long line of serviceable vehicles, even though most of them didn't drive each day. Complete waste of maintenance effort. We could actually save the maintenance costs by 11%, maintain the availability, and actually you could drive more. The maintenance costs were really important because although the support was by Mercedes, the first line maintenance was soldiers. 11% fewer soldiers to maintain the fleet. That means you can do something more useful with a soldier than putting air in the tyres and oil in the engine of the vehicle. You can get them doing military stuff, like shooting people and things, training. Significant benefit, even though the activity rate was completely unchanged. We then found that even though this was a really mature system with really mature data, we found two specific issues. Firstly, the air filter, replacing that was the most expensive maintenance event on the whole vehicle. They said, no it isn't. I went, yes it is. No it isn't. Yes it is. No it isn't. Yes it is. We then said, well, look, it's quite clearly that it is. They went away and they found that they had a data error. And the data error was back in the logistics support analysis record provided by Mercedes that said the part you need is not the air filter paper insert, but the air filter metal housing. So for years, people have been demanding the metal housing with the paper insert in it to take the paper out, throw the metal away, and put the paper into the engine. Because this data error had carried over into the illustrated parts catalogue, and therefore was what all the soldiers demanded. They knew this was going on, but it never got stopped. They had a massive pile of redundant scrap metal for air filter housing when all they wanted was the paper. Got that sorted. The second one is they said the central locking system was the second most expensive maintenance event on the whole vehicle. And they went, yeah, it is a real pain to us. But it's an intermittent software fault and Mercedes can't fix it, so we don't know what to do. Okay. Do you know how much you are paying for this maintenance event? It's that much. It's a lot of money. Can I suggest the next time you go to Mercedes to negotiate your annual support contract, you tell them that you're going to deduct this sum of money from their annual support contract until they've fixed this fault. The Swedish colonel started grinning from ear to ear. The problem was fixed in the next cycle by Mercedes because they realised what they were going to lose. So even though it was really old, really mature, used in a very benign way, we still managed to save 2.7% of the annual support costs. But much more importantly was there's 11% fewer soldiers, and you could do it with 70 fewer vehicles. So actually your fleet would last longer. There's an example that I've got on a different vehicle where they're driving certain vehicles up to 250,000 kilometres, and then the universal joint on the front axle needs replacing, but you cannot order a universal joint. You have to order a whole front axle. I said, why? I said, what do you have to do? I said, no. Why are you driving it so far that you have to replace the axle? You've got 70 vehicles in store in greaseproof paper that have not driven a mile. Drive these to 200,000, put those away, get the old one out, spread the life across the fleet that you bought. You shouldn't have bought it, but you have, and save yourself a fortune in support costs. Never thought of that. They'd never thought of it because they'd never had the access to the data. So I've shown you a helicopter, and I've shown you a vehicle. So the Swedes then said, okay, get you now. Please can you look at this vehicle? This is an 8-wheeled armoured fighting vehicle built in Finland, and it hasn't yet been delivered. So it's not in service yet. But what could you, though, give us the baseline for doing supportability audit in later life? Certainly we can. But we'll have a look whilst we're there. So we had a look at the data. And what we found is the same sort of thing, that the maintenance policies by location were just not sensible. And that we find ways of reducing the resources by 8%, which had an effect of reducing the cost by 2%. In other words, by not doing the maintenance in the places they said, but doing it in different places, it could save money before it entered service. The plan was wrong. Secondly, we went right through the data and looked at the data quality. And we said, I think you have a problem with your data quality in one place. They said, why? I said, how many wheels has this vehicle got? 8. How many tyres per vehicle? Per wheel? 1. How many tyres per vehicle? Well, 8. Yeah, but you've only ordered enough tyres for 1 wheel because your data is inconsistent. You have ordered 1/8 of the tyres you need because you said there's 1 tyre per vehicle when you meant 1 tyre per wheel. Well, we better fix that. They hadn't seen typical data errors that would have caused enormous problems as soon as they entered service. But we just went through the data and said, this is illogical. We also looked at the maintenance events and we came up with 6 specific maintenance events where the material cost drivers, the resources, suggested something ought to be done. And they went, what are they? I went, 1, 2, 3, 4, 5, 6. We already knew about 4 of those, and we have put in engineering change proposals or requests to Patria to do them, but we didn't know about the other 2. Thank you. So before the thing entered service, the digital twin was suggesting that the system needed to be modified, that the equipment needed to be changed, the maintenance policy needed to be changed, and the support package needed to be changed. Just by looking at the data before it arrived. So they confirmed most of these, we set up a baseline, and we still came up with savings of more than 2%. 2% may not sound a lot, but this is just on a planned data. So we protected the availability by identifying the data errors. Massive, massive benefit to the customer. So to sum it all up, and that's got to be changed, okay, supportability audit is a powerful technique. It's an analytical technique. It's not a model. It's not a tool. It's a technique that can find, assess, and quantify the business case for making support savings. You find them, you assess them, you quantify them, You filter them if you like, if you're not. You can apply it to most, if not all, systems. I'd be very happy to apply this to a bakery, or to a mine, or to a renewable wind farm, energy farm. It doesn't matter. Lots of different environments, technology and maturity. From something in service for 36 years to something that hasn't in service. From a vehicle to a helicopter. And I'd be happy to do any of the others. When you take the benefits from those examples and you extrapolate up across defence, we're talking serious money. Serious money. The sort of things that would solve budget unaffordability. It requires a small investment up front to build the first model. I accept that, if you haven't already got it, to build the first digital twin. But a programme supportability projects, where you take the savings from the first one, take some of them, build the next model. Take some of the savings, build the next model. Take some of the savings, build the next model. Would be better than self-funding. Why don't you? Why don't you do it? Why doesn't everybody do it? Supportability audit, interrogate the digital twin and use that to find ways of doing more with less. Thank you. I'm also going to introduce this slide to the presentation and use words such as bending the cost curve, because that's what it's about. How long did that take, Tim?
That was 101, so that was 61 minutes.
Okay, so that's about right. Thank you. Yeah? Okay.
いくつか変えてほしいことがある。ちょっとまとめさせてくれる。
He had some request or comment about that.
Sure.
Yeah.
But is that, get into the detail, is that broadly what you want?
Yes.
So if I presented that in Tokyo, you'd be happy?
Yes, very happy.
Okay. Right. Now let's do the detail of the questions then.
もう言った方がいいのかな。一つ目が